So we gave an example that you have 4 particles arranged in within a system, and each particle is is experiencing a gravitational pull from other particles. So that's say. So again, I'm just going to use that same example: M1, M2, M3, and you have your M4. We discussed that particle 1 experiences the net force coming from other particles. With the magnitude, you can calculate that F12, F13, F14, and then you just add them together vectorially, okay? And then you can find the net force acting on particle 1. Whenever there's a force, there's energy involved. So what kind of energy would this system have? If those particles are interact with each other, and so whenever you deal with arrangement within the system, what sort of energy is that? The separation or arrangement, the energy, the kind of energy that involves separation or arrangement of the particle within the system. Yeah? Potential, right? So there is a potential energy. So in other words, whenever there's a force, there's energy involved, and that energy usually is potential energy. So in this case, there is a gravitational potential energy involved within that system. How do we find out the gravitational potential energy within that system? And what symbol do we use? We use U, right? So that's U, gravitational potential energy. So this term is not foreign to you. You actually learned that before. But then when you learn that is within 2 particle system. One is the particle, one is the Earth. Now we're going to use a generalized form that applies to any particles, not necessary to just the math or just the Earth. So if you recall, gravitational potential energy. What is that expression? When you have a particle m, that's some distance above the ground. How do you calculate that gravitational potential energy? Huh? mgh, right? Okay. This only works when you're dealing with the particle and the Earth, or particle and So because you use the G here. So this is very specified. Okay, what you're going to learn now is that you have particles, and these particles, they are arbitrary, they have arbitrary mass. What is the gravitational potential energy involved within that system? Within the system, how do you find that? What is the generalized form? Not this one. So whenever you ask to find the gravitational potential energy, stop using that. That will not be applicable. You have to use what we're going to learn. And what expression would that be? We're going to derive it. So let me just write down that the gravitational potential energy of the 2 particles that interacting with each other is this. That'll be your G, M1, M2, and the separation between them, and it is negative. So your U here is equal to negative. So that describes the energy within particle 1 and particle 2 when they interact. That is negative G N1 N2 over R 1, 2. Do not square it. Do not treat this as a vector. We're dealing with energy. Energy is a scalar. Because in the past, students were very smart in a way that when they asked to find force, they just add those forces algebraically. When they asked to find gravitational potential energy, they treat them as a vector. So they had it. Don't laugh, because I actually say it every year. But then every year, I still have like a few students made that mistake. It's just so funny. And also when you're asked to find the gravitational potential energy within the system, the students are very inventive. Instead of using this expression, they will just multiply whatever particles that I have. So they have M1 multiplied by M2 multiplied by M3 multiplied by M4. You don't do that. You do it as a pair. You pair the particles. So this was interaction between particle 1 and 2, particle 1 and 3, particle 1 and 4, and so forth. You don't have n1 times n2 times n3. We don't have that question. We don't have that equation. Okay? The only equation we have to account for the gravitational potential energy within the system is Gm1 n2 over R12, and it's negative. The other difference between gravitational potential energy and gravitational force is that when we calculate force, we don't care about the interaction between other particles. But when you're calculating energy within the system, every interaction counts. So now you have to take into account these two are interact with each other. These two are interacting with each other. These two are interacting with each other. In addition to that, this two, and so you have to sum up all the possible interaction to account for the possible energy within that system. So let's see how many interactions are there. When I say interaction, it means that you have to pair particle. So that's in order to find each interaction. Okay. So for a 4-particle system, what is the net potential energy involved? So we have to pair them. So let's do a running pair. Okay. So you have U12. That's interaction between 1, 2. And then what? So we have 4 particles. So we run from 1, 2, and then 1, 3, and then 1, 4. That will be all the interaction between 1 and other particles. So 1, 2, 1, 3, and then 1, 4. In addition to that, we run off the pairing, pairing other particle with particle 1. Then we start with the sequence of particle 2. So now we have 2. We start with 2. We don't do 2, 1 because we already have 1, 2. 2, 1 and 1, 2 are the same. So you don't want to do double counting. So you have start from particle 2. You don't do 2, 1. So you have 2, 3. You have 2, 4. Okay. So you don't do 2, 2 because they do not self-interact. So you have 2, 3, and then you have 2, 4. Now, once you're done with the pairing, you don't have any other particles to pair with 2. Then we start with the sequence 3. So U3. 3, because you can't do 1, 2. You can't do 3. The only possible will be 4. And that will be it. Right? So for a 4-particle system, how many turns are there? You have 1, 2, 3, 4, 5, 6. There are 6 turns there to account for the total energy within that system. Okay? Any questions so far? Yes? We're going to derive that. So this is given. And then we're going to derive it why this is negative. Okay? So you have this, and then this is also the gravitational potential energy for, this is a general form. So this is the right equation. And the one, the MGH, that will be specific. That's, that describes the interaction between the particle and the Earth. This describes the interactions of any 2 particles. Okay? So we have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 2, 3, 2, 4, and then 3, 4. So this is a 4-particle system. And within this expression, so you will use negative G, M1, M2, and then you have the separation between them. Separation between them. So you have this, all this size, and you might have the diagonal length as well to go into the calculation. Okay? So this is when you have 4 particles, you have 6 turns. If you have three particles, let's say if we remove these particles, how many turns will there be? So if particle 4 is not there, how many turns will there be? So all the 4 goes away, right? So you only have 3. And that 3 will be 1 and 2, 1 and 3, and then 2 and 3. Okay? Okay? Are we good? And then so you treat after you use this equation to calculate each turn, just add them and numerically. Okay? And then whatever, so you should always get a negative value. You can't get a positive value because you start with a negative value. There's no way for them to be negative, so to be positive. So it's always a negative, you sum up all the negative. Okay? Now, so how do we get that expression? This expression was given, but it was not explained. So to answer that question, let's say if you have an object, I'd say this is, let me see. Do we want to use the mass? We can use that, and then we can. Let's say you just have. Let's use Earth as an example. Okay, so you have the Earth. You have the object that's some distance away. So let's say from the center to that distance. That's called the R. So we know that this object has mass m. We know that at any time this particle experiences gravitational force by the presence of the Earth, right? So you have your F, you have your Fg, experienced by this these particles. Okay. So what we're going to do is that if we want to move this particle to the edge of the universe, so this is very far away, some distance, and that's in the radial direction. How much work will be involved to move from this particle from this point all the way to some infinity? Remember, if the Earth is not there, this particle will not experience any force. So you can just move the particle anywhere. You don't have to do any work. But now, because there's an interaction between them, and that interaction is actually attractive, so if you want to move this particle away from these other particles, you have to do work in order for you to move that particle to place it somewhere. So the question is, how much work is involved, and why are we interested in finding out the work? Because we want to find the expression for gravitational potential energy. How is gravitational potential energy related to the work done by moving the particle from point A to point B? How are they related to each other? Work and potential energy change. Chapter 8. Huh? How are they related to each other? Work. The amount of work done is used to. Okay, let's start with the kinetic energy. So kinetic energy and work. What kinetic energy theorem? That you know, right? Delta K is equal to W. Yeah. What about potential energy change? NW. Negative. Okay, so delta U is equal to negative, right? Negative work done. So your work basically is transfer energy to or from the system, right? So delta U is equal to negative work. So that's why we want to find work. Once we find out work, then we can use this equation to relate how much work is done to the change in potential energy. So how do we calculate work? If you want to move from particle 1 from this point and then incrementally to infinity, which means that instead of just like use force times displacement, now you have to use calculus because the distance now is not just some separation, it's actually changes slowly. So we have to use, by definition, right? Or FDR, to be honest, to be rigorous. So we have your FDR. So what we're going to do now is that we're going to find out how much work is involved when you have a particle initial at point R. We're going to move it to infinity, and then the force experienced by this particle is gravitational force. So we have the expression. What is the gravitational force? The gravitational force. What is gravitational force? Using Newton's law of gravitation. Yes? Are we still using mg? No, we don't use mg now. Huh? Cosine. Hey, the very beginning, gravitation. Newton's law of gravitation, we use the force. You two have experienced gravitational force, right? And what is that expression? The capital G. Yeah, so you should abandon the mg. That would be, that would not, you would use a generalized form, GMM, okay? So you have G, M, M, and then over, let's say, R. So now R is a dummy variable, okay? Because you are going to move from one point to another. So you have GMN over R squared. Now, this gravitational force is downwards. What about the displacement? You're moving from this point to the infinity. So what is the direction of displacement? Upwards, right? So that's dr. So when you do FDR, what do we have here? G is downward, dr is upward, so they differ by 180 degrees, right? So when you have FDR, you have FDR, you have F times dr, and then times cosine of the angle between them, right? So that will be cosine 180, that gives you negative. So your work is negative, and you have your F and then dr, right? Okay, so now you have your F, which is G, capital N, little m, and then you have your dr, and then you'll have over r squared. And your r start from this point, capital R, to infinity. Any questions so far? Up to this point. So FDR, this is scalar product. So you have your, so this basically is the force, the displacement, and then cosine of the angle between them. The angle between them is 180, so that's why you have a negative sign there. And then you draw the vector sign, so you have F times dr, right? And your F has this magnitude, which is gmn over r squared. So gmn, they are constant, you move the outside integral sign, so you have dr over r squared. And integrate from initial position to final position. So what is dr over r squared? Do we know that? Most of the students should know, yeah? Negative 1 over r, right? After you do the integration, that will be negative 1 over r. And then you have a negative already, so double negative, that gives you positive. So you have your g, m, n, and then 1 over r. Okay? And then from initial to final position. So this is the amount of work. So on the right-hand side, you have your G, you have little n, you have capital N, you have over infinity, and then minus G, M, capital N over your R. So what is something over infinity? That's 0. So on the left-hand side, on the right-hand side, you have, so this basically equal to negative capital G, little n, capital N over your R, initial position. So that is the amount of work that needs to be done. Remember, the amount of work is equal to negative delta U. So we can set that equal to each other. So delta U is equal to, you have negative work, your work is equal to this. So negative, negative, again, that negative get cancelled. So you have your GMM over R. Delta U is defined as the final gravitational potential energy. So we use this, the final gravitational potential energy at infinity, because infinity is our final position, minus gravitational potential energy when you have initial position, right? Okay, and that's equal to G, M, N over R. Whenever we're dealing with potential energy, you have to choose a reference point. So here's what we're going to choose. We're going to choose this to be 0. So in other words, at the edge of the universe, it has no gravitational potential energy whatsoever. So so this term will be 0. So what we have here now is that your U at this point, we just have the magnitude of negative G, M, N over R. And that's how we got this. And that's the result that we used, okay, earlier. Okay, so this definition, this expression is with the understanding that we define the gravitational potential energy at this point to be 0. Because you have to have a reference point, and this is the reference point that we choose to be 0. So you get this expression that's negative GMN over R. Okay. So when you do a problem, it says that if we you want to find the gravitational potential energy of the system with with respect to gravitational potential energy to infinity when it's set to 0, it just basically means that you want to use this expression to calculate your gravitational potential energy. Because you have to have a reference point, and your reference point is set to be at infinity and has a value of 0. Okay? So, if you're not following this, the derivation, that'll be fine, but the key point here is that this is the equation that you need to use, need to know and use to find the energy. Okay? All right, so now since we defined the gravitational potential energy at infinity to be 0, so now we can actually look at a very interesting, phenomena. Let's say if we have a scenario, I mentioned earlier that we're earthbound, right? So there are many, through centuries, people have thought about how to escape from the Earth and go to other planets. But in order to go to other planets, let's say Moon, it's not like you can just go from here to there. There's some certain barrier they have to overcome in order to go from the Earth, in order to actually escape from Earth's gravitational pull and then arrive to other places. Okay? What is that bound? Why are we bound, earthbound? And it's because there's a gravitational potential energy involved, right? So if it's everything. When you think about all this scenario, energy is the key concept. If we have a device that has sufficient enough energy to overcome, to be greater than the gravitational pull, then of course we can just go from this point to that point, no problem. So it all depends on how much energy that this one has in order to overcome the gravitational potential energy. And if there's anything left over, then you can actually move away from the Earth's gravitational pull. So the scenario, or the process, is that how much energy is involved, and how do we account for the amount of energy that's required in order to have enough energy to escape from the Earth's gravitational pull. So let's look at this case. Remember, we said that you have to have enough energy. So let's say what is the mechanical energy involved, and everything has to be everything has to be conserved when it comes to energy. So let's say initial point, you have this energy. And let's say we want to go to the age of the universe. So let's say this is to infinity. So we know that the gravitational potential energy at infinity is defined as 0. Simultaneously, once you reach the age of the universe, hypothetically, that you lose all the kinetic energy, you will come to a stop. So what does that mean? It means that, let's say this is your final point, final destination. Then the total energy at this point would be, the total mechanical energy at the age of the universe would be 0, because we don't have any potential energy and you can't go any further, so you'll have to come to a stop. So there's no kinetic energy. It's all hypothetical. So we have a scenario that if you initially had this amount of energy, and if you want to go to the age of the universe, or the total energy at this point is 0. What does that mean? It means that the energy that it started with also has to be 0 as well. Although it's kind of difficult to conceive that you have a 0 energy system, but it doesn't mean that everything is 0 within that system. Within that system, you have kinetic energy, you have potential energy. Just like the sum of those two terms gives you 0. Okay? So it just means that initial energy and final energy has to be equal to 0. And initial energy consists of two terms, kinetic energy and gravitational potential energy. And at the age of the universe, we know that the whole thing is equal to 0. So from this, based on this requirement that energy has to be conserved, and there are two terms of energy involved, one is kinetic, one is potential, then you can actually find out how fast that this device has to have, what kind of speed that this device has to have in order to overcome the gravitational pull, just based on the conservation energy, arguments. Okay? So your K, you have 1/2 mass of the object, not the mass of the Earth. And then how fast? So that's V squared. What is the potential energy? that is on the surface of the Earth or any planets? What is the expression? Gravitational potential energy? What about UI? What is the expression?
Minus capital G, capital N, little n.
Okay, right? And that R is the radius of the Earth. Let's say this is, we're talking about Earth, so it's radius of Earth. And the whole thing should be equal to 0. Kinetic energy plus potential energy. And potential is negative. Okay, so in negative Gmn over R. So you can see that. In an ideal case, the mass of the object really doesn't matter. What matters, what determines the velocity, is the mass of this big object and the size of this big object that you're trying to get away from. Okay? So that's rearrange this, you get that your V is equal to 2 times gravitational constant, and then times the mass of the planet, and then over your R, and then you square it. So this is what determines. If you want to have a device to escape the gravitational pull, this is the amount, the minimum velocity that the device should have in order to escape, and that's basically, is proportional to square root of the ratio of the mass to the radius, the mass and the size of the planet. Okay, so you can actually calculate that, and you find that it's actually quite a large number. So you have to have so your device should be equipped with a pretty powerful energy system in order to achieve whatever you want to achieve, to escape from the Earth. Okay.